Okay. What else?
Distribution of mass density.
The moment of inertia?
That's what I'm going for. Moment of inertia. If I look at the formulas here. The moment of inertia of a solid sphere. Barely better. This is 2/5 mr squared. The hoop, mr squared. The hollow ball, 2/3 mr squared. The disk, 1/2 mr squared. When we did disk versus hoop, disk, gesh, versus hoop, which one won?
Yes.
When we did solid sphere versus hoop, which one won?
Solid sphere.
How can, if I did solid sphere versus hollow ball, or thin shelled sphere, which would win?
The solid ball,
Why?
because it is a smaller number.
Let's check it out. Assuming I find the ping pong ball. No. Cannot find the ping pong ball. All right. So I run that trial and you see that Courtney's right. If you miss it on the video, that's because you just weren't watching carefully enough. If we think about it, I have started out with all this potential energy and it gets converted into kinetic as it goes down. The kinetic energy is it's the moment of inertia about the center of mass plus 1/2 mv squared. The moment of inertia about the center of mass is definitely affected by that fraction up front. The bigger the fraction, the more energy that gets into the rotation, which means there's less left over for it actually moving down the ramp. That's the conceptual piece of it from an energy point of view. We, of course, can look at it from a math point of view, and we will. We'll just take one of them, we'll do a solid sphere. Because also notice that the radius did not seem to matter, and the mass did not seem to matter. It's just distribution of mass, so let's actually cover a couple of those things all in one. Make 15 meters, and we'll make it 37 degrees. 3, 4, 5 triangle. Not worried about the size of ball. From an energy point of view, I know energy initial equals energy final. Which does bring up a question though. This ball is rolling. What is required in order for there to be rolling? Okay.
Kinetic friction. Static friction?
Pardon?
No.
Say it again.
Well, I was gonna say kinetic friction, but
But then you changed it to,
static friction?
yes. If it were just kinetic friction, if only kinetic friction were involved here, that thing would just be sliding down like this. It wouldn't roll at all. It requires static in order to actually roll. But static friction, conservative or non-conservative?
Non-conservative.
Yeah, friction's a classic non-conservative. So I have a non-conservative force. Wait a second, this thing is moving in that direction and I have friction acting back that way. Why is no work being done? Because it's static friction. If you think about what static friction is acting on, if I have a wheel here, and I am looking at the motion at this point right here, this point is gonna move down, it's gonna touch, it's gonna come back up, down, basically at one point, it's gonna be moving like that. And there's a picture out in the hallway of somebody who did this with lights. Lights on a car wheel. The static friction at this point is acting back in that direction, but the motion of that point is perpendicular to that. Static friction is acting on a point that is actually moving down and then up, while the friction is acting horizontally. So the friction is not doing any work, assuming it is rolling. Then that's why I usually emphasize without slipping. Once you throw slipping into it, we now have non-conservative work involved. Okay, I plus. I'm gonna break the kinetic up. Instead of, I could just do, it's rotational, rotating about this point right here, but we've already gone through what's going on here. We have a 1/2 mv squared plus 1/2 I omega squared, where this is I is the moment of inertia about the center of mass. And this right here is the speed of the center of mass. Plus mgh, these are all initial. There we go. 1/2 mv final squared plus 1/2 I omega final squared plus mgh final. What can we get rid of? Pardon? Why?
Because we can set that equals 0.
Okay.
The initial loss is 0.
Yeah, I didn't state it here, we demonstrated it. This is 0, and for the same reason. And there we go. We've reduced it down to that. mgh initial equals 1/2 mv final squared plus 1/2 I omega final squared. We're dealing with a solid sphere. We have a formula that we can plug in here, so I have mghi is 1/2 mv final squared plus 1/2 times 2/5 mr squared, omega final squared. And mass goes away, and this is why mass doesn't matter. I have this r squared omega squared. What does that equal?
D squared.
Okay, assuming no slipping. GH initial equals 1/2 VF squared plus 1/5 V squared, VF squared. If this were just simply objects sliding down ramp, a frictionless ramp, that term would not be there. All the potential goes into getting that thing to move down. But we do have a rolling effect here, and so GHI, at that point, radius disappeared, that's why the radius doesn't matter. 7/10 VF squared, and so the speed at the bottom is the square root of 10 GHI over 7. This would be 2 GHI, again, if we're just sliding down a frictionless ramp. And so this becomes the square root of 10 times 9.8 times my initial height, which is 3, 4, 5, so 9 meters over 7. $100, 900, 7, something, so 1. What is it?
11.2.
0.2. Units.
I'm not sure.
per second.
Yeah, it's a speed.
I have a question, in that equation, because before I wrote 1/2 times the inertia times the angular
Speed.
speed
Squared.
plus squared plus that. So why is it now? It's just.
So K rotational was the 1/2 I omega squared. And this is how we defined omega, or, defined moment of inertia. This is about whatever the axis of rotation is. So if the axis of rotation is not the center of mass, then it's I center of mass plus this linear piece to it. When we did it before, I think we were doing a specific situation, a specific case.
Yeah, that situation.
Yeah, so we had a disk. And so, getting back to your question, what was your question again?
Oh,
Or do I?
yeah. So I think I wrote this.
Oh. You were right. Thank you. Yeah. Oops. Yeah, I did it correctly over here. And this is the moment of inertia about the center of mass.
So that's a rolling object, right?
Yeah, we're rolling objects. Now, just as a side note, before I let you go, this speed right here is the speed of the center of mass. Let's make sure I'm not an hour off here. No. That's the speed of the center of mass. This is the angular speed about the center of mass. When we, over here, when we set V is equal to omega r, this is the definition of rolling without slipping. If it is rolling without, if it rolls with slipping, then this falls apart in terms of that right there. So slipping would destroy this, as well as destroy that. And now, you can do the Rube-Goldberg test through part J. So when Thanksgiving gets a little dull, you just pull it out and say, hey, let's work this test. And then when they can't get it because they've never had physics, just look at them, like they're beneath you. It's family. Can't do it to family, who can you do it?
Have you ever done that with Thanksgiving?
No. No, I got trained early. I used to correct my wife's grammar. And then I found out not everybody grew up with their grammar constantly being corrected. She did not seem to appreciate it.
When you have a 9 in your root,
Because the height, 37-degree angle, it's a 3-4-5 triangle, my hypotenuse is 15 meters. So this should be around 9, this, the horizontal distance should be around 12. So technically the 9 is 15 times the sine of 37 degrees.
So the chapter 9 master set, like, for this,